All right, so chapter 6.6, inverse of matrices is what we're focused on. As you hopefully you'll see that it's just pretty much arithmetic, and you're not that intimidated by it. I don't know what to tell you. If I say it's not hard, you won't believe me. So, guess we'll just dive in. So we're going to understand a matrix inverse and the identity matrices. We're going to find inverses symbolically. Then we're going to represent linear systems with matrix operations. And we're going to solve linear systems with matrix inverses. So it's just another way to solve in linear systems using matrices, which at this point you'll have multiple ways of doing. So it's going to be up to you whether you want to use which one. So I'm going to be just straightforward. I know you're going to probably go and look it up and try to figure it out. I'm not going to go through the steps, but here are the steps that you can look back on and reference on how to do it in the calculator. I am not going to teach it to you. I just saved you the time of wasting your time Googling the internet instead of just doing your homework. But here they are. Try to make sense of it if you choose to. But we're going to go through it by hand. And yeah, so, but you can see it here. Okay. All right. So here we go. When you have a matrix inverse, so inverse is represented with an I. If you look at a one element matrix, inverse is just ones. If you look at a matrix, a 2 by 2, you'll see it's ones and zeros. And 3 by 3, you'll see that it's still ones and zeros. And then noticing that the ones are on the diagonal from top to bottom. And also notice that in order for it to be an identity matrix, it has to be a square matrix, which means that they're the same number of rows and the same number of columns. Do we see that? Okay. All right, so we're going to talk about determining if B is the inverse of A. And so to determine if something is the inverse of something else, it's pretty straightforward. All you're going to do is multiply. So we're going to do A times B. And if A times B produces the identity matrix, so if A times B equals 1, 0, 0, 1, and if B times A equals 1, 0, 0, 1, then that means that B is its inverse. Does that make sense? Now, if it does not, then they are not inverse. So if we remember from multiplying last week, when you're multiplying the row, the elements in each row by the elements in each column and adding them together, right? Elements in each row, add them together. Elements, okay? So we're going to try to see if it happens. So we're looking for a identity matrix for a 2 by 2. And so when we do A times B, we end up with 3 times 1 minus 2 times 1, 3 times 2 minus 2 times 3, and such. And we end up with our first identity matrix. Okay, all right, looking good, checking out. And then we're going to do B times A. And when we do B times A, we also end up with a 2 by 2 inverse matrix. And so guess what that means? They are inverses. B is the inverse of A. So it comes down to, can you multiply? How did you feel about the multiplication unit section of this? Did you seem doable? Were you okay? If not, then yeah, that's another story. All right, so now we're going to talk about, are we good with identifying before I move on? So identifying is just multiplication. Got it? And you want the results, the product to be the identity matrix. And again, it has to be a square matrix, meaning the same number of rows and same number of columns. Same number of rows, same number of columns. So now we're going to find the inverse of a matrix. And so to find the inverse, we are going to, I just had a brain fart. Transform it. So we're basically going to try to create it from here. So by using our row transformation. So, and the reason why is because we want to form a 3x6 augmented matrix with a 3x3 identity matrix on the right half. So what that looks like, where's my space? I didn't give myself any room to work. Pause. All right, so what we're gonna create is we have A equals, and that's our 0, 1, 0, 0, 0, -1, -1, 0, 0. And that's gonna equal 0, 0, -1, 1, 0, 0, 0, -1, 0, times, not times, I'm going to draw a line. I'm going to draw a line because I'm making a 6. Uh, 1, 0, 0, 0, 0, 1, 1, 0. Like that's all the zeros I need. Yes. So this is what it means to make a 3x6. And now with the 3x6, our goal is to use row transformations. And we want to basically take this left side and make it look like the right side. And what's left on the right side will be our inverse. So you're taking this and you're going to make it into a identity matrix. So the first thing that I would need to do here is probably just switch row 2 and row 1. So my first transformation is going to be row 2 switched with row 1. So by doing that, I end up with 1, 0, 0, 0, 1, 0, and 0, 0, -1, 0, 1, 0. No. Man. 1, 0. And row 3 was untouched. Okay. A next quick move here would be to switch row 2 and row 3. So I'm going to switch row 2 with row 3. And when I do that, row 1 is untouched. And now row 3, 0, -1, 0, 0, 0, 1. And row 2, 0, 0, -1, 1, 0. What's going on? Cool. 1, 1, 0, 0. Okay, so now they've almost completely switched. Then all that's left for me to do is to multiply rows 2 and row 3 each by -1. And I'm going to be lazy and do that in one step. Is that okay with y'all? So I'm going to take row 2 and multiply by -1 and row 3 and multiply by -1. And that's going to leave me with 1, 0, 0, 0, 1, 0, 0, +1, 0, 0, 0, -1, 0, 0, +1, -1, 0, 0. The right side is your solution. So the right side is now my solution. So that means that the inverse matrix is 0, 1, 0, 0, 0, negative 1, negative 1, 0, 0. So it's like playing a matrix puzzle game. I remember when I learned this, I thought about it like, have you ever been to Crackle Barrel and they have that thing where you got to jump over in the triangle, the sticks? You're like trying to move it around to get all the sticks where they need to be. That's what I think of this as, is I'm trying to move the pieces around so that what was once on the right is now on the left. Now, this one was a fairly easy one because it only included ones, right? So I just had to do a little bit of shuffling and the process was made easier. Now, if there was other values, it would be a little bit of a lengthier process. So we're going to do one without ones already present. So here we have A equals 4, 3, -3, -2. That means that I'm going to have to transform it into 1, 0, 0, 1. That's what I'm going to have to transform it into. So we're going to begin by making our 2 by 4 augmented matrix. And we're going to put our 2 by 2 identity matrix on the right half. And from here, we're going to start manipulating it. So that we can create only ones and zeros. So what do you think our first step we could do to start turning these numbers into ones and zeros? No suggestions? I know y'all like playing puzzles and video games and games on your phone. All right, well, what if we made a new row 1 by adding row 1 and row 2 together? Would that start turning some things into ones and zeros? That would, okay? So we're gonna add row 1 and row 2, and that made us turn into ones and ones. Okay? What can I do to here to keep getting ones and zeros? Remember, you can multiply and add to transform a row. I can add again, but before I add again, I need to do what? I need to multiply. So if I multiply row 1 by 3 and then add, look what happens. So the only one that's left that needs to be changed and instead of adding, what should I do this time? Subtract. So I need to change this guy right here to a 0. So if I subtract row 1 minus row 2, will this become a 0? Yeah. So if I transform row 1 by doing row 1 minus row 2, it becomes a 0. So notice how my left and right sides have switched places. What I'm left with on the right is my solution. So my inverse is -2, -3, 3, and 4. Nope. Nope. Not admitting any of that. Not admitting to any of that. I'm going to teach this full on, and what you figure out from here is on you. Okay? Okay. All right. Let's try a harder one. So we have a 3 by 3, and our goal is to become 1, 1, 1, 0, 0, 0, 0, 0, 0. That's ugly, but you get it. All right, so we're gonna make a 3 by 6 now. I don't know what the heck. Whatever, there you go. Okay, so our goal is to switch the left and right hand sides. What is our first plan of action? At row 2 and row 3, that could work, yeah. And one more thing that I can easily do to turn. What could I easily do to row 1? To turn this guy into a positive 1. Multiply by -1, right? So 2 birds, 1 stone. We're going to multiply row 1 by -1 and take Gio's idea and add row 2 to row 3 to make a new row 2. Okay. We got some 1s and 0s happening. We got our 1s on the diagonal, but we need to change -1, -3, and 2 into some 0s. What could I do, let's see, to turn -2 into a 0? Anyone? Everyone? Somebody? Somebody. What could I do to turn -2 into a 0? You can't add just to one row. You can multiply to just one row, but you can't add just one row. No one? Well, what if I multiply row 1 by 2 and then added it to row 3? Will that transform that -2 into a 0? Yes, it will. Okay. And now I'm like, oh, darn it, I have a -1. Well, that's an easy fix, right? Because that can be changed through multiplication. So if I multiply row 3, so I can change this back into a positive 1 by -1, it's going to change the signs of this guy and that guy. All right, I have 2 elements left that need to become zeros. How can I make those 2 elements into zeros? Yes, good job. Perfect. You are right on the money, Zane. And what's on the right-hand side is my inverse. What are your questions? Again, it's a puzzle. So how you may get to it may not be the same way. I'm a pretty direct person, so I'm going to try to find the shortest amount of steps to take. But are you going to necessarily take the same steps as I do? No, you're not. All right. So here we're going to talk about representing a linear system with a matrix operation. So we've already gone through how to use matrices and solve for linear systems, but here's another way to get to the same point as before. If you have a linear system or three variable system in this case, you turn it into a matrix. And then you set it up as a matrix operations, a matrix equation, where you're looking for X, Y, and Z. And so let's see what it looks like. So for this one, if it was a linear system, a two variable system, it would be set up like so. So basically you're asking yourself, what multiplies 2 times X plus negative 6 times Y is going to make 3, right? And then you'll have your 4 times X plus, it's just plus 2 times Y is going to make 6. That's why it works that way. Because it's just setting it up in terms of matrix multiplication. And that's it. So that's how you set it up. The setup is pretty easy. Now, do I 100% see the reason of solving it like this? No, because we've already talked about how to do it as a augmented matrix. But we're going to quickly go through it just so that you can see how to do it. All right, so essentially what you're doing here is you're finding the inverse. And the reason why you're finding the inverse is because when you're dividing by A, that's the inverse of A. So you start off with creating your matrix. So once you've created your matrix, you're now going to find A negative 1. So I'm going to take this guy and find its inverse. I didn't find it. All right. So finding the inverse here is, it's pretty easy when it's a linear. Zario may have mentioned before in my old life that I may have given y'all a tidbit of how to find it quickly. For the sake of being lazy, I'm going to do it again here. So when it's a 2 by 2, if you notice, all you're doing is switching your elements and changing their signs. It's kind of it. It's pretty easy, pretty straightforward. And it's just the ones on the diagonal. So instead of 8 here, it becomes positive 2 and negative 8. And then these are going to stay the same. Thank you for listening to me last year. It meant a lot. But yeah, but it's only for 2 by 2s. Does that make sense? This little trick is only for 2 by 2s. And so once you have that, then to find your solution, you're going to multiply it times what you have. So we go through the multiplication. And the ending results, that's your solution. So now you know that your X equals 2 and your Y equals 1, and your solution is 2, 1. Now, I see the beauty and the easiness of this if it's a 2 variable system. If it is a 3 variable system, I don't really see the purpose of doing it this way. Does it make sense? It's just more work for yourself than what we previously learned in 6.3 or in Unit 5. But here you go. So here we have this 3-variable system. We're going to take the system, turn it into a matrix. Here's the linear system written as a matrix. Then we're going to find the inverse of matrix A. So this is A, this is matrix X, this is matrix B. So our steps are 1, go from system. That's not how you spell system. Again, do I encourage this for a 3-variable matrix? No. But system to matrix in the format of A, X equals B. And then step 2 is find the inverse of A. And then step 3 is to multiply inverse of A times B. And that leads you to your solution. And those are your 3 steps that you're going to follow if you choose to do it this way. All right, so we're going to find the inverse of A. So you're going to find the inverse of A. And if you do it in the calculator, it's pretty straightforward. Here's your inverse of A. Bam. Any questions about putting in the calculator? Create the matrix and you put it to the power of -1. And it will do it for you. And then after you find the inverse of A, you're going to now multiply it times B. And again, if you put B in the calculator and you type it, it will multiply it for you. And then, therefore, your answer is 6, 2, and 8. Okay. I will tell you, I did not do it by hand because I feel like there are other ways to do it by hand that are more efficient than doing this method by hand. But yeah, so it can be done in the calculator. And that is it for 6-6.